All right, folks, thanks for tuning in. And what we're going to do right here is take a look at log transformations and specifically at what happens to the numbers. Because I think there's a lot of resources that will say, oh, just do a log transformation or try a log transformation, or just sort of throw it out so casually without really talking about what is happening to the numbers when that occurs, and that is the purpose of this video. So here goes. First things first, I'm going to set a seed value just to ensure code reproducibility, and what we're going to start with are some randomly distributed log normal values. And so we are going to get some right skewed data. The comment here is referring to something we'll do later on, so I'll push that down a little bit. And let's go with numbers because I'm feeling uncreative and can't think of a better variable name. We are going to say RL norm, and then we're going to get, we'll get 1,000 of them. And we'll go 0, 1, and let me run it. And there are some numbers. And so just to prove that that is going to have quite a nice bit of right skew, let's go hist numbers and take a look. Oh, that's looking mighty right skewed. So we can see that we've got this big bumper crop of values here between 0 and 5, a huge drop off down here between 5 and 10, and then some other outlier values further on down the line. But that is what we've got to start with. And we are going to see, well, what happens if we transform those values? So let's do that. And we're going to use a log transformation, and there's actually many possible log transformations. We could use, I mean, there's really infinitely many because we can decide the base value to use in a log transformation. So, and by base, what I really mean is we're doing an exponentiation process, but in reverse. But we're going to get to that. So we're going to use natural log, which uses E or Euler's number or 2.71828 something as a base. And let's do it. So let's call these logged numbers, and we're going to say log numbers. And now we have that, and now we can look at these, and let's see what they look like. And ta-da! Now we have gone from this very right-skewed data distribution to this very nicely normal looking, not perfectly normal, but that's okay. There's a little bit of noise in there, and that's fine. To this second distribution that we see right here, which is far more symmetric looking than the first one. And okay, fine, that's the, you know, that's what you see. But I said the purpose here was really to think about why that is in terms of what's really going on with the numbers. So let's take a look at numbers. I'll just print that down to the console, and we can see all 1,000 values down here. This was the original set of values. And what you see are lots and lots of values in that first bucket, that 0 to 5 bucket, many, many fewer between 6 and 10, and then some big outliers further to the right. We've got like the 12 something here and 10.92, 17 something down there. So what happens, and let's look at the logged numbers too, before we think about how these values are related. So the way these values are related is what the second set of numbers is telling us. What these values are is the answer to the question, if we used a base of 2.71828, and really it's a much longer number that goes on infinitely, but that's what we're going to abbreviate it to here. If we use that as a base, to what number would we have to raise that base in order to get that original value? And so to be a little bit more concrete and less abstract, let's use a value, and I'm going to use value number 972 right here. So 972, we see this value here, and what I'm going to say is we are going to see what is 972. Well, I'll store it up here so I don't lose track of it, but let's go down to 972 in the log numbers and see what's going on with that. And 972, where are you? 972 is right here, so 2.28, blah, blah, blah. Let me bring that up here. And what I want to say is, what is the relationship between these? And let's go, what we want to say is, so 2.71828, and if we raise that base, to this number's power, to that power, let's see what we get. And what we get is a number that is remarkably similar to the one you see there. And if you really wanted to see that, if you really wanted to see exactly the same number, you could use the exp function or exponential function, but that's not the purpose of this. The purpose of this is to really drill down and see, not just to say, oh, look, it just appeared, but to really see what the numeric relationship is. And so, yes, there's a slight difference due to the amount of precision in the actual constant e that I'm sort of just being a little sloppy by truncating here. That is the relationship. So that's where, and I won't bore you to tears by showing you that for every single value, but I promise you it will always work. So if you picked any value from the original set of numbers, and then you looked at its logged transformed counterpart, the relationship between them is this base to the log transformed counterpart value. It brings you back to the original number. But okay, then who cares? Why do we care? Well, one of the things about the log transformation is the impact that it has on outliers. The log transformation greatly condenses the distribution of data, the full distribution. And we could see that. To see that, let's look at the range function. So let's go range, we'll say numbers. This is the original set of numbers. And then let's look at range of log numbers. And what we see is a significant change in terms of the range. Think about the span of the values. As you see it very conveniently, the first one, I'll just sort of pretend that original number was about 0 and say that the range is about 32. In the second case, the range is considerably smaller. It's a very roughly about 7. So that's one big impact that it has, and that the reduction of the impact of outliers or the condensing of all the values can be good in terms of fitting something to a linear model where you don't have this like wild unpredictability caused by just a small handful of numbers. There's another important thing I want you to know though about this, and it has to do with something you'll see with a lot of right-skewed data, and this is a nice example here of right skew. So when you think right skew, left skew, I always want you to think of the direction of the tail. And with a lot of right skewed data, the values themselves are range bound. A lot of real world phenomena with right skew are zero bound. A good example of that is income data. There are some wild outliers, celebrities, hedge fund managers, movie stars off to the right. There's a lot of values that are going to be bunched up on the left side of that distribution, but there's no negative values. So the fact that they're range bound contributes to the shape of the distribution and the right skew that we see. And with other phenomena that are right skewed, if you look into what the data is all about and what it represents, you'll find similarly, you'll find many cases where it's range bound by 0, but perhaps it could be range bound by something else. The impact of the log transformation is that you're removing that break on the possible distribution of the values. So none of these values crossed the line, none of these values went below 0 in the original group. But let's come back to the impact of using that constant, that 2.71828 as a base. That means that when you have values like these, where some of the original values are less than 2.71828, the log transformed value of those is going to include some negative numbers, because we can take that base, raise it to a negative value, and still get a positive value, but we can get something smaller than the base itself. And that's not, even if something wasn't constrained by 0, the impact of the log transformation would still be to bring the data to basically unconstrain the data to the left side. And I'm going to show you that real quick, and then I'll wrap this up. But suppose just to show that and to show why 0 doesn't really matter that much, suppose I said numbers times, well, let me save this as another variable. I'll call this numbers 2. I'm going to say numbers times 50. And we can view that. So let's take a look at numbers 2. And now we've just taken the original randomly generated set of values, we've just multiplied them all by 50. So we have bigger values, but they're still distributed we're still getting that same sense of distribution, of that strong right skew. And then if we said log numbers 2, and we said log numbers 2, and we looked at that, log numbers 2, the impact of taking the log of that is still that we've come to a better place of symmetry. So even though in the case of log numbers 2, if you look at those values, none of them became negative, and that's okay. They didn't have to, but the boundary to the left, the constraint that was bunching them up in that direction is now not there anymore, because the impact of the log transformation, which you saw here, and you can check that out more on your own if you want to, gave us a lot of values that were to the left of where the original boundary was. So that is an important impact that log transformations have. And if you want to see more numbers, as I said, I won't drag it out and torture you by going number by number by number, but I really do recommend play around with it, try this yourself, and run a few values through and then look at what's happening, look at the impact on the big outliers, look at which values are taking on the transformed values that are to the left of the original set of values distribution, and you can get a sense of how a log transformation alters the shape of a data distribution. And thank you very much.